Let's just jump right in. What do the booming colors of a fireworks display, the buzz of a glowing neon sign, and the highly specific layout of the periodic table actually have in common? It seems like a stretch, right? But the secret to every single one of these lies in understanding atoms not just as solid chunks of matter, but as tiny, microscopic solar systems that follow a very strict, incredibly specific rulebook. Okay, take a look at this quantum blueprint. Now, I know it might look like a crazy, dense ladder of symbols and arrows at first glance, but honestly, it's a beautifully simple map. It shows exactly how electrons arrange themselves in energy levels, the shells and subshells, around the central nucleus of an atom. Just imagine the nucleus is the sun in our tiny solar system, and the electrons are the planets orbiting around it. Now focus on that energy arrow pointing up on the left side there. This is basically the golden rule of our atomic solar system. Lower energy equals more stability. And here's the thing you have to remember about electrons. They are essentially incredibly lazy. Given the choice, they strongly prefer to chill down in those lower, more stable positions. They're only going to venture up into those higher levels if all the comfortable, low-energy spots are completely full. So let's break this down a bit more. Every single little box on our map represents an orbital. That's just a three-dimensional space where an electron is highly likely to hang out. And those little up and down arrows drawn inside the boxes, those are the electrons themselves. So, an empty box, that simply means an empty orbital waiting to be filled. So, how on earth do we make sense of all this? Well, instead of getting bogged down in abstract, heavy math, just think of this entirely as an address system. You know how you have a country, a city, a street, and a house number to tell the mail carrier exactly where you live? Every single electron has a unique, four-part cosmic address made up of what we call quantum numbers. All right, the first part of our address is n, the principal quantum number. You can just think of n as the floor of a massive high-rise apartment building. It tells us the main shell or energy level. If n equals 1, you're on the ground floor, right next to the nucleus. If n equals 2, 3, or 4, you're moving up to higher floors. The bigger that number gets, the farther away you are from the nucleus, and the higher the overall energy of that shell. Okay, moving on to the second part of the address, L, the azimuthal, or angular momentum, quantum number. If n was the floor of your building, L is the specific shape of the neighborhood you're moving into on that floor. It tells us the shape of the subshell. If L equals 0, we call it an S subshell, and it has a nice, simple spherical shape. If L equals 1, it's a P subshell, which is shaped kind of like a dumbbell. And as we go up to D and F subshells, those shapes get incredibly complex and intricate. Next up, coordinate number 3, the magnetic quantum number, or M sub L. This one's important because it dictates the actual orientation in space. It's the reason why the spherical S neighborhood only ever gets one single box. But a dumbbell-shaped P neighborhood, well, that can point along the X, Y, or Z axes, so it gets 3 distinct boxes. And those super complex D neighborhoods we mentioned, they get 5. And finally, we get to the very last piece of our cosmic address, M sub S, the spin quantum number. Here's the catch. Even if two electrons share the exact same building, the same floor, the same neighborhood shape and orientation, meaning they are living in the exact same little box, they still need one final way to be distinct. In the quantum world, an electron only has 2 possible spin directions, positive 1/2, shown as an upward pointing arrow, or negative 1/2, shown as a downward pointing arrow. Okay, so we've got our 4-part address system totally locked down. But you can't just let millions of electrons move into these cosmic neighborhoods however they please, right? They have to follow extremely strict rules of real estate. And getting a grip on these rules is absolutely the key to unlocking how atoms interact with each other. Rule number 1 is the Aufbau principle. Aufbau is just a German word that means building up. Imagine the atom is a massive movie theater. When the doors open, people naturally want the best, most comfortable seats at the very bottom, closest to the screen, right? Well, electrons do the exact same thing. They fill the lowest, most stable energy seats first before moving up. They start at 1s, fill that completely up, then move to 2s, then the 2p section, then 3s, and so on, building from the bottom to the top. Now, because of the seating rule, we get this fascinating little quirk of nature. If you follow the energy levels up past 3p, wait for it, the 4s box actually sits at a physically lower energy level than the 3d boxes, even though it's technically a higher shell number. So, those lazy electrons will actually sit in the 4s seats before they even begin to touch the 3d seats. It's a beautiful, kind of messy reality of quantum mechanics. Now, this is absolutely crucial. Once these electrons start moving into those empty orbitals, there's a strict capacity limit. Any single box maxes out at exactly 2 electrons, no exceptions. And if 2 electrons are going to share that same tight 3D space, their spin arrows absolutely must face opposite directions, one pointing up, one pointing down. And that brings us right to the Pauli exclusion principle. Think about it like a bus. 2 people can't sit in the exact same seat on a bus, right? Well, 2 electrons can't have the exact same state. They need different spins to coexist in that same orbital. This one principle guarantees that absolutely no 2 electrons in an entire atom can ever have the exact same 4-part quantum address. It's literally the ultimate rule of microscopic individuality. So up until now, everything we've talked about is what we call the ground state. That's the lowest energy, perfectly settled, most stable arrangement possible. But look, the universe isn't static. What happens when atoms get blasted with energy from heat or light? Well, those perfectly seated electrons absorb that energy, and it literally causes them to temporarily jump up out of their cozy, low-energy seats and into higher, empty orbitals. They get excited. But remember our golden rule? Electrons are lazy. They crave stability. They absolutely cannot stay up in those high-energy states forever. So what goes up must come down. When they inevitably fall back down to their cozy ground state, they release all that extra energy as spectacular bursts of light. This tiny, microscopic plunge is the exact mechanism creating the brilliant booms of fireworks in the night sky and those mesmerizing dancing lights of the auroras at the poles. It is literally quantum mechanics scaled up to a breathtaking visual display. Honestly, it is just incredible to zoom out and look at our macro world through this microscopic lens. Like, why do these quantum numbers even matter? Well, because they are the invisible architecture of everything. They explain why the periodic table is shaped the way it is, because it's literally just a map of how these electron shells fill up. They explain chemical properties, why sodium is so crazy reactive, while neon is perfectly stable with full shells. From the glow of a neon sign to the precision of lasers and the functioning of all our modern electronics, it all comes back to these very rules. Let's put this whole picture together real quick. We've got our 4 numbers. N gives us the shell and the overall energy. L gives us the specific shape of the subshell. M sub L gives us the orientation in space, and M sub S gives us that crucial spin direction. Keep these 4 things in mind, and you essentially have the ultimate decoder ring for understanding the chemical universe. I want to leave you with this one final thought. Knowing what you know now about this cosmic address, the strict rules of the quantum neighborhood, and those crazy energy leaps of electrons, the next time you look up at a bursting firework or walk past a glowing neon sign, will you just see the light? Or will you see the millions and millions of tiny invisible quantum leaps that are actually making that spectacular light happen? I really hope this explainer has sparked a whole new way of seeing the everyday world around you. Thanks so much for joining me, and keep exploring.